Today we're going to keep talking about magnetic force and get to some of the, what I think are some of the most interesting aspects of magnetic force, including a topic called motional EMF. And we'll see what that is in a minute. To review, what I want to do is share screen. So to review where we've gotten to so far, talking about magnetic force, we found that magnetic forces affect only moving particles, moving charged particles. That the force on one particle was given by the equation magnetic force is equal to QV cross B, where this is V is the velocity of the particle, and charge is the charge of the particle, and B is the applied field, which means a term we use to mean the field due to things in the surroundings. So the field due to things in the surroundings. And it's clear from the equation that the magnetic force is perpendicular to the velocity of the particle. And it's also perpendicular to the magnetic field. So it's captured best by a cross product. We also saw that since there are moving charges in a current carrying wire, so force on a current carrying wire of length delta L was given by the same equation except multiplied by the number of charges in that piece of wire. And that came out to the conventional current delta L cross B, where delta L is, as usual, in a vector in the direction of conventional current. And we looked at various applications of this, and you're exploring applications of this in lab this week. I want to consider now a situation in which we have a neutral conductor moving through a magnetic field. So let's consider a situation where we've got a magnetic field out of the page here. And we have just a bar of metal. It's neutral. And you're dragging it at speed V to the left through this magnetic field. Now, is there a magnetic force on this moving bar? So we have a bar, neutral metal bar moving in a region of where there's a non-zero magnetic field. Well, the bar is neutral, it has no charge. So clearly the net force on the bar is 0. So is there any reason that the bar would have any charge distribution on the surface? Well, no, it's neutral, right? But let's consider a situation where we consider one electron inside the bar. Now that electron is moving to the left with speed v in a magnetic field. So in fact, it will experience a magnetic force. We have, and let's think about the direction of the magnetic force. We have v to the left. So we point our fingers of our right hand in the direction of v. We curl our fingers out of the plane. V cross b is up. And that means, but this is an electron, so QV cross B is down. So in fact, we have a magnetic force on the electron that actually is down. That suggests that the mobile electrons in this bar are going to experience a magnetic force. And since they're free to move, they're going to move down to the bottom of the bar, making the bottom of the bar somewhat negative. Now, there of course is a magnetic force on the positive atomic cores in the bar, but they're bonded to other positive objects and they can't move. But on the other hand, we now have a deficiency of electrons at the top of the bar. So the bar actually polarizes. Due to the magnetic force on the mobile electrons. Well, that's interesting. What would happen if we drag the bar the other direction? So let's have the same bar. We have the same magnetic field here out of the page. But this time we're going to drag the bar this way with its speed, constant speed v. Now if we consider one electron in the middle of the bar, v cross b is now down, so qv cross b is up. So we have magnetic force on the electron up, and we're going to get negative charge on that end of the bar and positive charge on that end of the bar. So it looks like, what does this look like? Well, it actually looks like a battery. So we just made a battery. We could ask, what is the EMF of this battery? And what good is it? What can we do with it? And indeed, we'll be able to calculate its EMF, and this whole phenomenon is called motional EMS. Motional is called motional EMF. So polarizing a moving bar, a moving conductor in a magnetic field. So in order to calculate the EMF of this battery, we have to think about the steady state. So here's our Here's our magnetic field out. Here's the bar. Here's the electron. And we have a magnetic force up on the electron because the V is to the right. And at time t equals 0, when we just start dragging it, there is no charge accumulated on the bar. A little bit later, the bar is still moving. Sometime delta t later, the bar is still moving to the right. And now we have some positive charge accumulated on the bottom and some negative charge accumulated on the top. And notice that now the forces on this electron have actually changed a little bit. So we have this magnetic force on the electron, magnetic force on the electron that's up. But now we also have an electric field inside the bar here due to these charges that are the polarization charges. So now we have, let's make it a little smaller. We have a small electric field inside the bar. And so we actually have a small electric force on this electron as well. But the net force is still upward. The electric field hasn't got big enough, so we'll go on a little while longer. T equals T plus 2 delta T or N delta T or something like that. And you can see where this is going to go, right? You can see that eventually we get to a situation where we've accumulated enough negative charge on the top of the bar and enough positive charge on the bottom of the bar that now the magnetic force on an electron up is completely balanced by an electric force on the down due to this electric field from the polarization charges. And then the bar is no longer going to polarize anymore. Polarization is actually done. So what about a non-conductor? Well, if there are no mobile charges, would the object polarize? Since there are no mobile charges, even though there'd be forces on the charges, they wouldn't be able to move, and so we wouldn't get any polarization, and so we wouldn't get any motional EMF. And so in fact, this would only work if we have this works only if the material is a conductor. So how do we figure out what the EMF of this battery is? Well, what is the EMF and what does it depend on? Well, we see that when we get to the steady state, we're still going to consider our single electron as the system. At the steady state, where the bar is still moving, but it's not polarizing anymore, we have the magnitude of the magnetic force on the electron is equal to the magnitude of the electric force on the electron. The magnitude of the magnetic force is just the charge times the speed times the magnetic field times sine of 90 degrees here. And this electric force is, of course, just the charge of the electron times the electric field inside the bar. This is this electric field due to polarization. And when that happens, we don't get any more polarization, and we've reached this steady state. And simplifying this expression, we see that VB, the electric field inside the bar, is going to be equal to V times B. So therefore, bigger V gives us a bigger E. Or a bigger applied magnetic field also gives us a bigger electric field. So knowing the electric field inside the bar, we can get the potential difference across the bar. So what is delta V from one end of the bar to the other? So this is the potential difference we're interested in. That potential difference between the ends of the bar. Well, delta V is just going to be the electric field in the bar times the length of the bar. So this bar has a length L. And of course, this is equal to VBL, since E is equal to V times B. Now we know that in a battery, the magnitude of the potential difference is equal to the absolute value of the EMF. So that should give us the EMF of this battery we've created. So the EMF of the battery, the polarized bar, is equal to VBL. Now, in the steady state, so this bar is moving along at speed V. What's the net force required to keep the bar moving at speed V? Well, it's zero, because there's no dissipation here. So zero net force needed to keep the bar moving. So if you're in outer space and you have this bar near in a region of magnetic field, you can just give it a shove and it'll coast along forever in this polarized state. So what can we do with this motional EMF? Is this useful? Well, it could be useful. So let's think if we could use this polarized bar as a battery to actually make a current run in a circuit. So using motional EMF to drive a current. Now, a moving bar is a slightly awkward battery to use. So what we're going to need to do here is make up a circuit where we've got a metal rod here and another metal rod here. For the bar to slide on. So our bar is gonna slide on these metal rods here. And we're gonna start it moving, excuse me, to the right, speed v. We're gonna have a region here where there's a magnetic field out of the page everywhere. And to make the circuit do something useful, we'll put some kind of resistor here, maybe a light bulb with resistance R. So think for a minute, in this case, about what direction conventional current is going to flow in this circuit. So the bar is going to slide to the right with negligible friction. So the bar is sliding on these rails to the right with negligible friction through this region where there's a magnetic field out of the page here. Well, let's record the polarization of our bar here. We have V cross B is down, so we have negative charge going up. So what we got before, yep. And leaving a deficiency of negative charge down here. So if this is our battery, that must mean that in the wire, the electric field due to the battery is going like this in the circuit. Obviously, we're going to need a bigger electric field in the resistor here and smaller electric fields in this bar. So we have conventional current following the electric field and going clockwise in this case. Now, note, of course, that inside this bar, we actually have an electric field that points the wrong way. And so for current to flow through this bar in the wrong direction, conventional current, we definitely need some energy input. So notice that to make this work, we're going to need energy input. Because current has to flow the wrong way through the bar, the battery. Well, that was true before. That's what batteries do, is they expend energy to maintain a charge separation across themselves. Now, as current flows here, of course, the charges on the ends of the battery get depleted slightly. So as current flows, the electric force becomes just slightly smaller than the magnetic force, and the magnetic force can keep things polarized. So as current flows, the electric force is just a little bit less than magnetic force, just slightly. So F mag keeps polarizing the bar. Now, we talked before about batteries with a quote, non-Coulomb force. So in a battery to maintain a charge separation. Well, in this case, our non-Coulomb force is just the magnetic force. It's not a force due to electric fields, and that's, of course, equal to, in magnitude, to EBB sine of 90 degrees. Now, how much work per unit charge is this, quote, battery doing? So to move a charge to polarize the bar, well, the work is just the magnetic force times the length of the bar. And if we divide this by the charge on an electron, we get that the work per unit charge put in by this this non-Coulomb force is the velocity, the speed of the bar times BL, and that's the EMF of the battery. So that agrees with what we found above. And notice that still the round trip potential difference has to be 0. So we have a potential difference BBL across the bar. We're going to have a potential difference VBL across the resistor as well. So let's think about an example. If we move a wire from our electricity kit, so move a clip lead past the magnet in your kit, so here's the magnet from your kit, and you move a wire, say, out of the board. What would the EMF you'd get in this wire be? Well, let's see. Near the magnet, the magnetic field of the magnet was something like 1/10 of a Tesla. It's not a very big magnet. And let's say that you can move the wire at about 10 meters per second. And what's the length of the region of wire that's actually affected by the magnetic field of the magnet? Well, the magnetic field of the magnet, of course, gets weaker as you get farther away. So we'll say the length affected, that length, we'll say the length is about 1 centimeter. So we'd get VBL would be 10 meters per second times 1/10 of a Tesla times 0.01 meters, which would give us about 0.01 volts. So not enough to light a light bulb. So to make this practical in a real, so this is a baby generator. So what we've made is a generator. The way a generator usually works is we take a loop of wire, say on an axle. No, that's the skating one. And and in a magnetic field, and we just rotate the loop so that we turn the loop. So instead of having to keep running to slide a bar on rails, we could actually stand in one place and turn a crank to make a loop rotate through a magnetic field, and we'd get EMF. And if we wanted to make it bigger, we could add more turns of wire, so we could make a generator that way. But let's think about energy input. Are we getting something for nothing? Now you're probably thinking, no, we can't. And that's correct. So let's think about how that works out. So here's our circuit. Here's our rods. Here's our moving bar. Here's our resistor. We have magnetic field out in our example here. We have E this way. Bottom of the bar is positive, the top is negative. And now we have this conventional current flowing that way through this whole thing, including through this moving bar. The question is to think about is there a magnetic force on the moving bar? Well, the bar is neutral, so there's not a force because it's moving. But now there is, because there's a current flowing through the bar. So we have this current flowing this way, and we have magnetic, so we have I and delta L is going that way. We have a magnetic field out of the board. And so remember that the force on a current carrying wire is I delta L cross B. So we have delta L down, B out. Looks like we're going to get a magnetic force on the bar, and now we've changed systems. So now our system is the bar, not one electron. But we now have a magnetic force on the bar in a direction opposite to the bar's motion. So if we don't do anything, we give this bar a kick, it's just going to slow down and stop because of this magnetic force on the bar. So where does the energy come from to keep the bar moving? Well, you have to put in energy to keep the bar moving. So we're not getting this for free after all. So the magnetic force on the bar is going to be ILB sine of 90 degrees. And so we have this magnetic force on the bar, and therefore you have to exert a force equal and opposite to that to keep the bar moving. So the system is expending kinetic energy to run this current. You don't exactly expend energy to make a force. What happens is if we consider this entire circuit as the system, we're putting energy in. That energy, where does that energy get dissipated? Well, it gets dissipated in the resistor. So basically, the energy input that we put in is getting dissipated in the resistor. The light bulb glows, it gets hot, we see light. So our energy input gives energy to the electrons in the wires, which then lose energy in the resistor. Is basically how we're thinking about the energy flow in this system. So let's think about power input. So in a time delta t, we move the bar a distance delta x. So power is work over time. So we have the force by U times the distance you move the bar in some time delta t. And that's going to be equal to the force by U times delta x over delta t. But delta x over delta t, that's just v, the speed of the bar. So the power, your power input is the force you exert times the speed. We know how big the force you exert is, though, because the force by U is just equal to this magnetic force on the bar. So this is going to be equal to ILB sine 90 degrees, which is of course 1. So that's going to be equal to ILB times the speed of the bar. And the power dissipated by the resistor. So the power dissipated in the resistor is going to be, we saw that was going to be I delta V from chapter 19, which is I times the EMF, because these conducting rails are very good conductors and we don't have a big electric field in there. So that's I times a VBL. And these two things are equal. So our power input is equal to the power dissipated in the resistor. Okay, I want to talk briefly about magnetic torque. If there are magnetic forces, and this is, we'll practice with Motional Emf in recitation. We'll do some problems with that in recitation today. We've seen that there's a torque on a magnetic dipole. You've seen a compass needle is a small magnet, and you see that it orients in a magnetic field, so it twists one way or the other to align with the net magnetic field. So in a magnetic field, there's a torque on a magnetic dipole moment. And the torque acts in such a way to align this magnetic dipole moment with the net ambient magnetic field. So if we have a magnetic dipole moment pointing up and a magnetic field from the surroundings pointing up, this is a stable situation. But if the magnetic dipole moment is pointing down and the magnetic opposite to the magnetic field, this is an unstable situation, and the slightest jar to it will make the moment rotate back. And it turns out that the expression for torque is magnetic torque is actually given by the expression for mu cross B, where mu is the magnetic dipole moment. So let me remind you about magnetic dipole moments and how we get directions. We saw that various current configurations were magnetic dipoles. So if we have a loop with conventional current running, what have I got it here, counterclockwise in a plane here. The magnetic field due to this loop, look at the center of the loop, the magnetic field due to this loop is up, and the magnetic dipole moment points in the direction of the magnetic field along the axis. So this is also the direction of mu. Now, let me remind you how you can get the direction of the magnetic field due to a current loop. So let's look down on our current loop. Here's I. we want to get the direction of the magnetic field at the center. So at this location, we have a delta L, and we have R hat, and so dl cross R hat gives us a magnetic field due to this current loop at the center out of the page. And that's true no matter where we choose our delta L. So if we choose a delta L over here, we've got R hat here. And so that contributes in the same direction. So the entire loop contributes in the same direction. And for this current loop, the direction of the magnetic field at the center is also the direction of the magnetic field on the axis. So magnetic dipole moment is in direction of magnetic field along dipole axis. And that's true for a magnet too. So if we have a north and south, we have magnetic field coming like this. So the magnetic dipole moment of the magnet also points in that direction. Now for a current loop, remember that the absolute value, the magnitude of the magnetic dipole moment is just the current times the cross-sectional area. For a magnet, the magnetic dipole moment is the sum of all the atomic dipole moments. It's easiest to see how this magnetic torque works if we consider, if we actually consider a current loop. So let me either draw one or find a picture of one here. Try to draw it. So here is a current carrying loop that's supposed to be perpendicular to the page here, and it's mounted on an axle. And in this region, there's a magnetic field out of the page. And the current in this loop is going in this direction. So let's think about what the forces are on this current loop. Now it's easiest if we draw a side view. So I'm going to draw a side view looking at the edge of the loop. So here's the edge of the loop. At this end, we have current going into the page, and at this end, we have current coming out of the page. And the magnetic field is so the magnetic dipole moment of this current loop, since the current is going this way, the magnetic field due to the current loop is actually like that. But let's talk about forces. Let's think about the force on this end of this of the loop. We're going to have a magnetic force IDL cross B. So IDL is into the page, B is up. And so in fact, there's going to be a force that actually stretches the loop here. And on the other end, on this end, the left end, we have current coming out of the page, magnetic field up. So the magnetic force on this end, due to the current, it's that way. And if we think about this force, we can write it, we can draw it as the, sorry, that was not the direction of the magnetic force. Let's try again. I cross B is actually a force that way. And that way. But we can see that this is part of this force is just stretching this loop, but there's a piece of the force that's actually turning it. And this component of the force gives us a torque. Remember, torque is R cross F. So here's our R cross F. So it actually is a twists the loop. Now it works out, this is derived in the book, I'm not going to go through it now, but if you actually look at it and work it out, see derivation in the book, the torque actually does come out to be U cross B. There's a potential energy associated with this. Because since the natural configuration is magnetic dipole moment aligned with the ambient field, and the unnatural configuration, you have to put in energy to make this happen, is opposite to the magnetic field. So this is low energy. This is high energy. And it turns out that the magnetic potential energy is equal to minus mu dot B. So that's mu B cosine theta. And this also is derived in the book. I'm not going to go through it here. An application of this is magnetic resonance imaging, where you use the magnetic dipole moment of protons in a big applied field. And what you can do is find where the protons, you measure the amount of energy required to flip the magnetic moments of protons so that they're opposite to the applied field. So questions about that? Okay. since our quiz is available all day and you have a couple of tries at it, I'm experimenting with different quiz formats. I'd like to take a few minutes to talk about something completely different that's actually, I think, fairly interesting. And it's magnetic forces in a moving reference frame. And to do this, we're going to start out thinking about two protons that are just moving along at speed v. And of course, these two protons exert forces on each other. So we're going to call this proton 1. We're going to call this proton 2. And of course, so let's calculate the force on proton 2 due to proton 1. So well, first off, we have an electric field that's made by proton 1. So proton 1 makes an electric field E1. And we know that the magnitude of E1 is just 1 over 4 pi epsilon 0, the charge of the proton divided by r squared, where that's the distance r. And so the electric force on 1 is just going to be E1. So that's going to be 1 over 4 pi epsilon 0 E squared over r squared. However, particle 1 is, since it's moving, it also makes a magnetic field at the location of proton 2. So here's our r hat. V cross r hat is into the page. It's a positive charge, so QV across r hat is also into the page. So we have a magnetic field due to particle 1. And the magnitude of that magnetic field is mu 0 over 4 pi QV times the magnitude of r hat, which is 1, times the sine of 90 degrees divided by r squared. So we get a mu 0 over 4 pi QV over, let's make this an E, because we know it's a proton, so EV over r squared. And now we have a magnetic force on this proton. We know that this was the electric force, but there's going to be a magnetic force, and that's going to be given by EVB1 sine of 90 degrees. And let's find the direction of this magnetic force. V cross B means that there's a magnetic force upward, actually attracting the other proton. And so this was on 2. So force magnetic on 2 is equal to EV times B1, which is mu 0 over 4 pi EV over r squared, which gives us a mu 0 over 4 pi E squared V squared over r squared. Now, what's the relative magnitude of these forces? Which one is bigger? Well, let's just calculate the ratio. So F magnetic over F electric is equal to mu 0 over 4 pi E squared V squared over R squared divided by 1 over 4 pi epsilon 0 E squared over R squared. And if we cancel some things, let's see what cancels. E squared cancels, the R squared cancels. We get a V squared divided by 1 over 4 pi epsilon 0 divided by mu 0 over 4 pi. And that gives us a V squared over, well, this is 9 times 10 to the 9th Newton meters squared per Coulomb squared. And this is 1 times 10 to the negative 7th Tesla meter per ampere. So we get V squared over 9 times 10 to the 16th. Which is equal to V squared over 3 times 10 to the 8th squared, which is V squared over C squared. So in fact, the ratio of these forces depends on the magnitude of the speed, the velocity compared to the speed of light. Now that's interesting. How did the speed of light get into this? It just sort of fell out. Well, let's take this a step further and think about what observers see when they see these, watch these protons. So Alice and Bob are the names of 2 different observers that are used standard in the relativity discourse here. And so Alice and Bob and Albert Einstein are going to watch our protons moving, but they're going to do it a little bit differently. So here are our moving protons. They're moving with speed v. And we have these 2 forces acting on them. We have electric forces and magnetic forces, and our observer Bob sits still. So Bob sits still. And what he sees is that these protons move apart, but the electric force is bigger than the magnetic force. So they follow trajectories where they curve upwards and downwards until they hit the ceiling and they hit the floor. On the other hand, Alice runs along with the protons. So here are our protons. They're moving at speed v. But Alice also moves at speed v. So to her, in her reference frame, the protons aren't moving, and therefore there are no magnetic fields. So what Alice sees is only these electric forces. And she sees these protons just go straight up and hit the ceiling, or straight down and hit the floor. Furthermore, she sees a bigger F net, whereas Bob sees the net force is going to be the magnitude of the net force is the electric force minus magnetic force. So let's think about what they observe. Because both Alice and Bob have watches. So Alice and Bob synchronize their watches. And time this process. So Bob, who sees a smaller F net, finds that it takes 20 nanoseconds for the particles to hit the floor and the ceiling. So how's the magnetic force pointing upward? Okay, so remember that there are two steps in this. First we had to find the magnetic field at the location of B1, B2, the magnetic field at the location of proton 2 due to proton 1. So we say we have the velocity is that way, r hat is that way, it's a proton, so V cross r hat produces this magnetic field here into the page from due to proton 1 at the location of proton 2, okay? Now, given that magnetic field, we have to calculate the magnetic force on proton 2. And so the magnetic force is EV cross B. So if we point our fingers in the direction of V, then we have to curl the fingers into the page. And so our thumb sticks up in the direction of the magnetic force, which is an attractive force. Does that make sense, Hendrik? Okay, so we've got this net force. Bob sees a smaller net force. It takes him, he sees the protons taking 20 nanoseconds to hit the ceiling and floor. Alice sees a larger F net, and she times this, and it only takes 15 nanoseconds. Oh, yeah, it's easy to confuse the symbols, so it's important to remember that that's in and that's out. So the two of them actually think this process takes different amounts of time. How can that possibly be? Well, this is actually the problem that really puzzled Albert Einstein. And in fact, his paper on special relativity is actually entitled "On the Electrodynamics of Moving Bodies." It's about electric and magnetic interactions of moving objects, moving charged particles. And his conclusion was that the only possible thing that could be true, I mean, there's only one physical process going on. There's only these two protons. they can't hit the floor and the ceiling twice, it must be that the measurements are different because the time actually runs differently. It runs slower in a moving reference frame. And so both Alice and Bob were correct. Bob observed 20 nanoseconds in his reference frame. Alice, who's running along with the protons, observes it taking only 15 nanoseconds. And so in Alice's reference frame, time is moving slower, and her watch is actually running more slowly. And in fact, by the end of this time, Alice is actually aged only 15 nanoseconds, where Bob has aged 20 nanoseconds. So Bob has gotten slightly older than Alice. Now, there are some experimental tests of this that prove that this is really true. And a very interesting application is the case of muons. Muons are leptons. They're like electrons. They're slightly heavier than electrons. They're charged, depending on whether it's a particle or the antiparticle. They can be plus or minus, just like an electron and a positron. And they're not subject to the strong force. Muons live about 2 microseconds. So about 2 times 10 to the negative 6 seconds, and then they decay into other particles. So why doesn't Alice have a magnetic field? Because, so imagine that you're Alice, and you're on a skateboard moving along with these protons, but everything in the room is dark and the protons are illuminated. So all you can see is the protons. You can't see the floor or the ceiling or so you don't see anything passing. All you see is the protons. Well, the protons are just right beside you at all the time. So to you, in your reference frame, the protons have 0 velocity. And Eric, what the principle of relativity also says is that the laws of physics have to work in every reference frame. So they're true. And in a moving reference frame, relative to you, the velocity of these protons is indeed 0. And so that means that for Alice, she makes a correct observation, gliding along on her skateboard, right beside these glowing protons, which to her are not moving. And so, in fact, in that reference frame, if she takes out a compass, she will not measure a magnetic field due to either of these protons, because relative to her, they're not moving. So in any reference frame, you may observe something different, but it's internally consistent within your reference frame. It would be completely inconsistent in your reference frame if you did see a magnetic field and nothing was moving. So the principle of relativity says that the laws of physics apply in any reference frame, even if what you observe is not the same in different reference frames. We talked about this a little bit last year when we talked about pushing a book across a table on a train, where to the person in the moving train, they only did enough work to push the book across the table because they only pushed it a distance of, say, 30 centimeters. But to a person standing outside the train, the person didn't just push it across the table in the train, they pushed it through the entire distance the train moved, plus that distance. So being a moving reference frame does change what you observe. And so, so in a moving reference frame, Alice is, to her, the protons aren't moving, so she's not going to see a magnetic field. But to Bob, who's sitting still, well, and that's an interesting thing. I mean, that's the funny thing. That's the weird thing about magnetic fields, isn't it? That magnetic fields are one of these things where fields permeate throughout space, but you still have to have a particle to be the source of the field. So if there is no moving charge, then you don't see a magnetic field. Well, because, so why does the electric field not depend on the reference frame? And the reason notice that the equations, and we should have been kind of suspicious about this. So the equations for the electric and magnetic fields of charged particles are quite different. And we should have been suspicious about this from the beginning, because this one doesn't have a V in it. But this actually depends on the speed of the particle, and therefore it depends on whether something is moving or not. And remember, we actually talked about that way back when we were talking about magnetic fields, when we talked about somebody holding up a charged a piece of charged invisible tape in the front of the classroom. And you guys sitting in your seats didn't see a magnetic field from that because it wasn't moving. But if I ran past the tape was moving with respect to me, so I did see a magnetic field. So now it's completely, it's a very interesting thing to wonder about this velocity dependence, this motion dependence. You'll find in the textbook, and there are actually equations that show the transformations of magnetic and electric fields from one reference frame to another. So if you look in the book, you'll find they're called the Lorentz transforms, and you see the transformations of electric. What you'll see with electric and magnetic fields in different reference frames. We're out of time, but these are good questions, and these are things that Einstein and people since him have thought real hard about. So why is it like this? This is a pretty intriguing piece of electric and magnetic fields and electric and magnetic forces. So we're out of time. Don't forget to do the quiz sometime today. Don't forget to do the lab. Only 18 people have done it so far. Make sure you type your name in chat for attendance. And I'll see you guys next week.